Excellent. Okay, we're ready to roll. Okay, so again, welcome everybody to the Monsoon Seminar Series. We're back from a few weeks pretty much off for the seminar series. So please remember to type in your questions to the speaker so that we can go through them at the end of the chat here for those of you attending by Zoom. And then I will call on you to either read out your own question and you can ask it yourself, or if I don't hear from you, then I will read it off myself. So without further ado, we are welcoming here Dr. Geanina Butiseacă, I think. Apologize if I butchered your last name again. Who recently, I think, finished this research that she'll be telling us about from the Senckenberg Biodiversity and Climate Research Center in Frankfurt. And so again, without further ado, I will let her take over the speaking here, and she will talk to us about the late Miocene Paratethys.
Thank you, Tara. Okay, shall we? Yeah, so I don't know how many people are actually aware about Paratethys or what Paratethys means. So I'm going to split my talk into two parts. The first one, I will explain basically what is the Paratethys system, how it evolved, and what's the general context of it. And then the second part, I will discuss specifically about the impact over the Eurasian climate as we see it from the data that we produced. So the Paratethys is actually a large epicontinental sea that has its origins somewhere in the Oligocene. And it was so big that it was actually stretching from Germany to China, and it was covering a lot of actual countries. So we have actually France, Germany, Austria, Hungary, Slovakia, Serbia, Romania, Moldavia, Poland, Ukraine, Russia, until really to the border of China. Yeah, it formed many millions of years ago, as I was saying, in the Oligocene, but in time it started to shrink as the Tethys Ocean was closing completely, and as Africa pushed more and more towards north, all this area between Africa and the Eurasian continent was actually stuck together, and this is how we actually got the Alpine Himalayan belt. So Paratethys, it's somehow connected with the history of the Alpine orogeny, and in fact it was not a unitary basin, but actually a sort of puzzle of multiple basins that were in the end stuck in between these tectonic blocks. If we are looking in detail, we will see actually how big it was. It was even bigger than the Roman Empire, as I like to say it. Why is this Paratethys so special? As I was saying earlier to Tara, before I started working on the Paratethys, I wasn't really aware of how nice it was. But I think that Paratethys is special from many points of view. First of all, it's probably the largest epicontinental sea that has ever been, and its evolution is connected intimately, I could say, with the humidity source for the Eurasian continent. So the surface that was occupied by Paratethys as the water volume influenced a lot the precipitation patterns and the precipitation volumes over the Eurasian continent. As I was saying earlier, it's not a unitary basin, but a gathering of a lot of smaller basin ones. And they were connected continuously until around 12.6 million years ago. After this point, the isolation gets to be more intense, And this has a result, as a result, protracted endemism and diachrony, because all these basins are formed in different periods, and then they are filled in different periods. So we kind of get a little bit of chaotic stratigraphy. The Paratethys started to close, as I was saying, during the Miocene, and pretty much until around 13 million years ago, the western side was completely continentalized. So what we have today as the Alps completely closed the western basin, and we were left during the late Miocene only with the central and the eastern part. The central part covered pretty much what we know today as Central Europe, while the eastern Paratethys stretched from what is pretty much Romania and Black Sea until Kazakhstan. And the central Paratethys was connected very nicely at certain point with the Mediterranean through the Trans-Tertian corridor. And the connection between the two basins, the central and eastern Paratethys, was facilitated by two other straits. They have very local names, Berlad and Carasu. They are both at the border with Romania. And another gateway that actually was closed a bit earlier is the Mesopotamian gateway, which was active through Iran. And through this gateway, the Paratethys was connected with the Indian Ocean, through which occasionally fauna was passing into the Paratethys. As the tectonic collision continued over the late Miocene, during the Messinian, the Paratethys ended up as just a big lake, and it was completely disconnected with the other basins. And as we can see, it was also cut off from the Mediterranean, which in turn was cut off from the Mediterranean. So the tectonic situation from the late Miocene kind of brought a dark age over the Eurasian water bodies. I was also saying earlier that the stratigraphy is a bit chaotic in the Paratethys. This is a simplified sketch with the local stages and the paleontology they used for delimiting the stratigraphy. And as you can see, it's pretty different from one side to the other. For me, this was completely puzzling. When I started to work in this, I couldn't just understand it. Like, what is this? But it makes completely sense, because you have a lot of small basins and they all acted differently, and they had their own fauna, and everyone has its own climatic imprint, actually. Further, I will discuss about our results, the latest results that we have from the Eastern Paratethys. We have published a paper that is called Severe Late Miocene Droughts Affecting Western Eurasia. And this paper actually had several goals. First of all, we wanted to build a long-term viable data set for the late Miocene from the Eastern Paratethys, because no one has done it before. Actually, I think that using the tools that we use, no one has ever done it before to any of the Paratethyan basins. In the Black Sea, there are two other records from Geanina Butiseacă, one of my supervisors, but they are a bit younger. And with this one, we wanted to go deeper in time and cover as much as possible. We also wanted to see what changes are in hydrology and in the evaporation and the humidity of the basin. We tracked also vegetation changes with everything that is happening around the basin. And we also wanted to see what is the biomass burning presence by analyzing charcoal. But my favorite one is obviously the impact over biota, because the Paratethys had a great impact on the biota populating it, and of course all the other animals and plants living around it. And lastly, sorry, what was the overall Paratethys impact over the climate? The section in coast, it's called Panagia. It is situated in Taman Peninsula in Russia, on the northern margin of the Black Sea, and currently is not accessible anymore because in the last years a port was built and some other facilities. So we were really lucky actually to get these samples. From the image, you see a dotted contour with black. This is the late situation of the Paratethys. And if you're looking further, we have also a gray contour with the initial contour of Paratethys. So it's pretty much a situation from how we started and how we are going. So the areal extent of Paratethys changed so much that at the end of the Miocene, it was probably like only 20–30% of the initial volume. In terms of stratigraphy, Panagia section covers several local substages. The lower part covers a bit of Conchian. This starts around 13 million years until 12.65. Then Volhynian until around 12 millions, and then Bessarabian and Chersonian, the last stages of the Sarmatian local stage, which goes until 7.6. And then we also have a little bit of Miocene, which starts around 7.6 million. As you can see, the entire succession is clastic. Dominant are clays and marls, but we also have intercalations of carbonatic stuff. There are normal carbonates and also dolomites. And from a previous paper from one of our colleagues, he saw that some of these carbonates are associated actually with periods of drought. So this is very interesting, keep it in mind. Now further I will explain the tools that we are using actually to do all this climatic assessment. And we used mostly biomarkers, molecular compounds, and further we analyzed the isotopes on these compounds, and additionally we did some charcoal. So as you see from the image, the Paratethys is surrounded, of course, by some land. The alkanes that are produced by the plants around the hydrographic basin, they are carried by wind or by water into the basin, and they are sedimented together with our sediments. Some other components, they are produced in the water column or in the soils or on the water surface. And together with these, they are registering the climatic signal from the moment of formation. The evaporation, of course, it's also registered in the hydrogen isotopes, and we can assess with this method how dry or how much evaporation was at a certain point or how humid it was. I will explain short on what each biomarker in part means, because maybe there are people that don't know it. The first things that we used were leaf waxes. They are extremely precious because they are very resistant to biodegradation, but actually they are very simple components that are found in the cuticles of every vascular plant. Their role is to regulate the water loss and the gas exchange with the atmosphere. Thus, they are really useful for the plants. And most important, they are plant specific, which means that every plant has its own biological signature. So we cannot mistake the paleo reconstruction. Another nice tool is the using of alkanones. Alkanones are metabolic products of haptophyte algae, and in general they populate aquatic environments. So the oceans, the seas, lakes, they are all populated by these algae. And they like to spread everywhere, and when they have a lot of nutrients, they are actually blooming. And when they are blooming, we also found a lot of alkanones in the sediment. But the nice part with them is that they are actually sensitive to salinity and temperatures. So we can use them as thermometers or as salinity indicators. Cultures have shown that they react to the environmental stimuli very well. And it was even an index based on them that gives us temperatures. We didn't use them for temperatures for this section, but we use them to see the changes in evaporations and precipitation. The other components that we used are the GDGTs, glycerol dialkyl glycerol tetraeders. They are also used as thermometers because they are very abundant in all kinds of environments. They are more complex molecule, and they are used for two types of temperatures. The isoprenoidal, which are mostly aquatic. Actually, they are aquatic. They use for surface temperatures, while the branched GDGTs are used for mean air temperature. And as you can see, they are mostly produced by these little guys, the Termarchaeota and Crenarchaeota, but there are also some other groups that produce them as some of the eukaryotes. So they are very, very, very tiny things that are produced in the water column or in the soils. And they are very well preserved during the millions of years. And we can use them further to calculate various temperatures and also pH, because the signal, the continental signal, it's also calculated through pH. Further, we purified all these components, and we measured the carbon and hydrogen isotopes. We did this because, for example, the carbon isotopes on plants, they give us very good indications of what kind of vegetation mix we have. Values that are more negative will indicate a dominant C4 composition, while values that are more positive will indicate more C3 plants. So the C4 plants are actually the grasses mostly, and the other ones are in general superior plants like trees or shrubs. So we have a very clear delimitation in between what is open land vegetation and forests. The carbon isotopes on alkanones, it's also important, are also important because algae are behaving pretty much as plants. So they exchange with the water the carbon through CO2. And we can see, actually, we can reconstruct the paleo CO2. Further, we also measured the hydrogen isotopic composition on both alkanes and alkanones in order to assess, of course, the changes in vegetation, and also to see the relationship between the organic components and the water source. Because I was really interested in all this part of vegetation and vegetation reconstruction, I also decided to quantify the charcoal from our samples in order to see how much vegetation actually burned. And it was a really nice experience. Now to get to the results, finally, I will explain first what's happening in the marine domain, what we observe, and then I will go to the continental side. From temperature point of view, we see that the variability is pretty high, which was expected because the entire section, it's almost 5 million years. But we are going to focus on the upper part, because on the lower part we have several sedimentation gaps, and we were not so sure what's happening here. So until around 9.8 million years, we see no big changes actually in the temperatures, but around 9.7. We have a drop in temperature followed by a really high peak. So at this moment, we think that we have actually an influx of warm water in our basins that could signify actually a connection with another basin. After this moment, the temperatures are dropping again, and they remain pretty much low until around 7.8, when again we have a high peak in temperature of around 26 degrees. And until the end of the section, the temperature is dropping again until even 10 degrees. In terms of alkanones, this is really interesting. Until the same point, when we have the higher sea surface temperatures, we have no alkanones in the area, except these three appearances. But anyway, they are too low for measuring any isotopes. And after 9.65, they start to appear in our section, and actually they become really abundant, as you see from the productivity, until the end of the section. The hydrogen isotopes, they show us three dry intervals. One is centered at 9.65 and the second one at 9.28, while the third one is appearing at around 8 million years. In between the second and the third episode, we have a more humid interval, and also a smaller one in between the first and the second dry episode. So we interpret them as dry episodes because the hydrogen isotopic values indicate very high evaporation. Now in the continental domain, what we see, it's really interesting also because again, the first part of the section doesn't register much changes, but around 7.7, again, the vegetation starts to change. So whatever is changing in the marine domain, it happens also in the continental. And the carbon isotopes suggest actually a complete change in vegetation towards dominant C4. And after that, when this period corresponds with what we see as a dry and high evaporative period in the marine domain. followed by a replacement of vegetation yeah, this is more forest vegetation, so towards more C3, correspondent to the wet period that we were seeing on the hydrogen isotopes on alkanones. The last part of the section has a higher variability, as we were seeing also in the other side. In terms of mean annual temperatures, we see that the high temperatures on land, they are pretty much the same as in the periods when there are high temperatures in the sea, except some intervals. But overall, they are suggesting pretty much the same changes. The pH, it's pretty much mimicking, to say so, the mean annual temperature until 9.6 million years, after which is doing completely the opposite. So the higher the temperature, the more acid it is, which is normal if we are thinking also with what is happening today in the seas and with the global warming. If we are taking a step back and looking at all these sets of data, we can see that actually they are all indeed correlated. And I'm going to focus again on the upper part because here we have continuous data. And together with our data, the temperature and the hydrogen, we plot also some of the pollen data from Razumkova from 2012. And we can see that in the moments where there is an increase in temperature and evaporation, there is also an increase of pollen quantities of plants that prefer the dryness. Also, if we are looking at charcoal, we can see that there is also an increase in the fire activity. And the same happens in the upper part, so from around 8 million years. And in between them, as I was saying, we have a period with a lot of precipitations, and in this interval, we have very few or no dry taxa at all. And this is very interesting to me. There were some more data, but I haven't plotted them with some forest taxa. I see there is a question in the chat. Ah, okay. Okay. Besides our three drying events, another colleague of ours identifies a fourth one at around 9 million years, but we don't see it. So this can be due to the resolution of our samples. We don't know for sure, but he identified it based on the presence of carbonate intervals. So it's possible that indeed there is a fourth one here. Yeah. Just a moment, I got stuck. I will stop. Can you hear me?
Yes. So is your screen frozen?
Yes.
Okay. Is there maybe unshare your screen and then retry that, or is it completely?
Yeah. I will stop sharing. And how am I sharing it again? Share screen again. And I will go directly to the slide.
Yeah, let's see if that circumvents the problem.
Yeah. Yes.
Huzzah! Excellent.
Yes. Yeah. So the overall idea of what I talked about earlier is that we have these three main moments when we see a very intense drought haunting the eastern Paratethys, and in between these intervals we have rainy periods. And a little sketch to understand how this works. So in the first image, we have the situation of the Black Sea North Panagia section, disconnected from the other basins around. We don't know exactly how the North Aegean looked like. We have some hints that it might existed at that certain point. So if it existed, it must have been connected with the Mediterranean at a certain point. And when this disconnecting happens, the eastern Paratethys water level drops. It's also a drop, of course, in the precipitations, but it's also a crisis induced over biota. When we have a negative budget, a water budget, we have also intense stratification, and this can cause occasionally anoxia, which has a very high impact over the biota populating it. But also a drier environment makes possible the expansion. Yeah. Okay. Makes possible the expansion of C4 vegetation, which is more flammable and it burns more. In the periods where we have more precipitations, the basins can get reconnected, and again, certain animals, for example, can pass from one basin through to the other, and the vegetation starts to recover again, and we go to more C3, so the forests are coming again. This is not that good. A nice sketch made by Palco et al. In 2021. In the left panel up, we see how actually Paratethys changed its salinity from being a marine basin to pretty much a mega lake. And this happened when it was connected with the other ones, the other basins. But then when it got disconnected, it started to be partially desiccated. And this desiccation, as I was explaining in the previous slide, had a major consequence over the basin topography in general and the biota. Automatically, due to evaporation, some salt started to accumulate also in the basins, and he thinks that actually the Black Sea was a very salt lake. If we are looking further at other data around the Paratethys, we have also some precipitation data compiled by Böhm et al. In 2008, and they used the herpetofauna, the snake fauna from various sites of Europe, as a tool to reconstruct the precipitations. And what they found is that actually for Central and Eastern Europe, we have a very humid climate from approximately 11.3, 11.4 million years until 9.7, exactly the moment when the crisis also start in our section, to say so. So this is what we see also in Taman Peninsula. Until after this point, the precipitation drops and we have these dry intervals, followed by an interval where things start to come to normal and become more humid, and then it gets dry again. They are also looking further. For example, this is a data record from the Atlantic in the ODP 926. And in the Atlantic further south, they see two really high intense precipitation intervals centered this time at 10 and 9 million years. So it's a bit different than what we see in the rest of the Europe. We went even further and we tried to plot all the available temperature data around Eurasia, and we found that actually what is happening in the Eastern Paratethys and the Black Sea Kuban area where our section is, it's quite different than what's happening in the rest. So we don't really see many correlations. Maybe, I don't know, maybe some local things, like for example, here what's happening at 9.7 might be from the Atlantic something. But the idea is that the signal in general is very different. And probably if we will go to every major basin or every basin of Paratethys, we will see a completely different thing because they evolve differently. So all this isolation and endemic conditions, they led to a different climatic signal and pattern over the time. As a summary, the Taman section covers pretty much 5 million years. And why it's important is that because it basically witnesses the isolation of Paratethys. So until around 9.6, we see this connectivity and open basin hydrology. And after that, when it starts to be disconnected, we see the apparition of drying intervals all around the area. When the major changes are happening at 9.7, the alkanones are also kicking in. So this is possible to be a connection with another basin, and we were thinking about it because at 12.65 and 7.8, when we have pretty much the same signal in the SST, there are some other connections that we know about, so they are documented. And we were thinking that this one might be a third one, but probably it was a very short-lived connection that brought in very warm waters. But probably this connection brought in not only warm waters, but also alkanon producers. Because as I was saying, until this point, we don't really see them, but after 9.65, let's say 9.7, they not only appear, but they really thrive, to say so. So this could be an adaptation also to the Paratethys, maybe because it's isolated in some areas. Due to increased evaporation, the salinity increases, so these taxa mimic, actually the conditions are mimicking the conditions in the open ocean. We don't know exactly because we actually don't have any traces of alkanon producers. We know only about some Cocoletus, but it appears in the record before our alkanon productions. So it's possible that the producers in this case are non-calcifying haptophytes. Another major point from this section is that we witness the onset of savanna type vegetation in the Black Sea region, and other papers are documenting it, actually spreading from east to west from China and from south to north from Arabia. So we see basically the replacement of the evergreen subtropical woodlands with savanna type vegetation in the eastern Paratethys. Also very important is that the fact that the drier intervals from Panagia coincide with periods of mammal turnover in Eurasia and mammal dispersal. So what we know from the literature of the as the Valesian crisis or the Tyrolean fauna can be actually driven by these prolonged drought periods. So when it's very, very hot for a period of thousands of years, tens of thousands, the animals automatically are moving towards better places. So it's not literally a disappearing of the taxa from the paleontological record. It's just they are moving in another places with better conditions. It's like what's happening today in Africa, for example, when we have the migrations from Serengeti Plain. And another very important point close to my heart is the situation of the marine mammals that populate the Paratethys. Because of all these changes in connectivity and salinity, whales and dolphins and other big animals that were thriving in the Paratethys before, they start to enter in decline. And all this decline meant not only having issues with finding food, but they also shrinked. So they became dwarf in order to cope with the lack of resources in the basin. They suffered a while, to say so, and at the end of the Miocene they are going completely extinct, so the environment is not able to support their presence anymore. And this happens not only to the mammals but also to other species like bivalves and gastropods and some other animals. So what we see actually, it's accumulate signal and the repercussion of the Paratethys shrinking, it's affecting all the area around it also. And it's actually possible that the extent areal reduction of the Paratethys might have actually enhanced the evaporation and the dryness in the area. To take away from this study, I would say the most important part is that we have a strong regional imprint on the climate patterns. So as I was saying, what we see in this basin, in the Eastern Paratethys, it's mostly a regional signal, but added to the overall Paratethys situation, it starts to make more sense. The active tectonics and the protracted insolation, it might have enhanced the negative water budget. I was explaining with the surface reduction. Another major consequence might be over the water mixing, because the connection with other basins stops. Also, the water mixing has a lot to suffer. Maybe another very important point is the fact that the myth of Paratethys marks also the continentalization of Eurasia, or at least the part that was occupied by Paratethys, and the onset of open vegetation. So what is the death of something is the birth of something else. The death of Paratethys led to Europe as we know it today, pretty much. Yeah, I think in big lines, this was what I wanted to communicate to you. And thank you very much. I'm waiting for questions, and I've added here a small caption from a very nice paper that I read some days ago. They are illustrating the dispersal of Vishnu Onyx otters from India to Germany. So these little guys travel through Paratethys from India to Germany. Thank you very much.
Thank you.
Thank you. So we'll let some of the folks here type in some of their questions that they have for you. I'm honestly astounded about those otters.
Yes, because I didn't know about the otters that they existed actually in this area. It's really amazing, yeah. And I was imagining reading the paper. I was imagining the otters, you know, like taking their luggage and going to Germany. It's silly, I know.
Oh, I just had a question. Oh, and I just lost it. Oh my gosh, that's pretty embarrassing. It'll come back to me in about 15 seconds, I'm sure. We have one question here in the chat from Kate Wachowski. Kate, do you want to ask your question?
I can see it.
Oh, okay. So what Kate is asking is, how can you tell whether the delta 13 of carbon of the C29 alkane are reflecting C3 versus C4, or if that's a change in PCO2?
Yeah, so the 13C of N-alkanes are reflecting the C3 versus C4, and the PCO2 is actually reflected by the 13C of alkanones, and also the productivity, and their values are reflecting the vegetation composition in the case of N-alkanes, and in the case of alkanones are reflecting the PCO2 and productivity. Yeah. I don't know if I answered. So they are the two reflecting different things.
We have another question from Adam Forte. So Adam, do you want to ask your question out loud?
Yeah, sure. Can you hear me?
Yes.
Okay. Yeah, so it was a really interesting talk. At the end, you mentioned that like active tectonics might be sort of influencing some of the connections and changes in connections. I'm just curious, over the time interval that you're looking at, did you have specific tectonic events in mind that you think might be influencing the connections?
Yeah, and this is very amazing actually for the Paratethys, because we are witnessing the emergence of pretty much all the orogenies that we see nowadays in Europe. And I'm talking about the Alps, the Apennines, Carpathians, a part of the Balkans, the Caucasus, and all these emerging orogenies, they are automatically blocking the connection between the basins. Of course, we have also smaller scale events. Let's say, let's take as an example the connection in between the Black Sea and the Aegean and the Mediterranean, for example, on the North Anatolian Fold. So here we have just the plates sliding one over the other, but in the case of the other origins, the connectivity is completely obstructed. And not only is obstructed, but the sediments that are eroded from the mountains that are rising, they're also filling the basins. For example, in the Dacian Basin, which is in Romania, we see pretty much about 5 or 6 kilometers of sediments eroded in the last 5-6 million years. So it's really crazy.
Okay.
Hi, Ghana. Can you hear me?
Yeah.
Yeah, go ahead.
My question is that from your talk, I just take one question. That is, what is your lab methodology for this research? As you explain this research in detail, so what is the lab methodologies for this, such as you discuss isotopic study, isotope study, hydrogen isotopes, carbon as well. So my question is that what is your methodology of research? I'm from Pakistan.
So I think I didn't hear it properly. Can you
Hello?
repeat?
Could you repeat your question, please?
What?
Could you ask your question? It's your connection's a little hard to hear.
Okay, I send on chat as well. Now can you hear me?
Yes.
Yes.
Now can you hear me?
Yeah.
Hello?
We can hear
Yes, we can hear you.
My question is that I have just one question as from your talk. That is, what is your methodology for this research? Methodology, lab methodology.
the methodology, what I'm using.
Yeah.
Mm-hmm. Okay.
Yes.
Yeah. So first of all, for the big chunk of data, I am using the biomarkers, the lab procedures. I can send you a link if you want with the papers. So we collected all the rocks. We extracted them in the lab using sock sleds, and then we fractionated them. We split them in various fractions, one fraction for the analkane, one for alkenones, and one for the GDGT polars. And further, we measured them separately. And depending on the results and the cleanliness of the samples, we further measured the carbon and hydrogen isotopes. The first batch of work was done in Frankfurt, and the second one with the isotopes, it was done in EOS because we don't have this these machines. They are more complex and expensive for our budget.
Thank you very much. Thank you.
Yeah, no problem. And the charcoal was also done in Frankfurt by me.
Okay.
So we have another question by Jerry Dickens. Jerry, did you have time to ask your question? Because you mentioned you needed to catch a train.
Yeah, so how much, okay, so how much of the records reflect local versus global changes?
Yeah. Sorry, I'm just off the train right now. Want to hear you.
I hope you get your train in the end.
Thanks for the talk, though.
Yeah. So what we see on the first part of the section, it's a more general signal. So the same things happen over a larger context. But then after 7.7, 9.7, 9.6, when this basin that the section is situated in isolates, the situation starts to change really dramatically, and I think we are registering the local signal only, at least in terms of sea surface temperature and what's happening in the basin itself. But if we are looking at analkanes and the carbon isotopes on the analkanes and the charcoal, in this situation they are reflected in a more extended areal, as if because they are all these components, they are actually carried from all over Paratethys. So they are carried by rivers and winds, and the surface that they are covering, it's much larger. So I would say that we see a part of the local signal and a part of the more general signal too. Yeah.
Excellent, great. And you actually answered part of the question I was going to ask you in your response to Jerry just there, which was I was going to ask about different thresholds that might exist in your system because in this balance between, well, maybe you're catching kind of this more regional signal for a while until you reach this tipping point, and then within your basin, especially in terms of your water signals that are held within essentially your water records, that maybe after you get to a certain point, then things kind of get maybe out of control. And especially when you get into the drying and desiccating periods. But anyway, that was kind of related. It's more of a comment now rather than a question.
No, but it's true. Of course, it'd be very, very nice to go and test at least all the other basins. But I have the feeling that we are just at the beginning, you know, because there aren't many things using these proxies done. Of course, there are a lot of paleontological data, both mammals and plants. And people have tried to do various stuff, I think for 50, 60 years now, but using molecular compounds, no one has ever done it pretty much until the last years. I think Juliana is the pioneer, Juliana Vasiliev, and I am following her.
Okay, thanks. I think that is good for now. We've asked you a few questions. And so before everybody runs away, let's please give Geanina another hand for her excellent talk this week. So thank you for that. And sharing lots of things, excellent things about the Paratethys, excuse me. And so again, before everybody runs away, if you want to receive any emails related to this seminar series, please shoot me an email, Peter Clift an email, or Olivia Joson an email, and we will add you to the mailing list. And then second thing and last thing, make sure to stay tuned for Schedule B next week on the 17th of November, where Yama Dixit will be telling us about some of her latest research. And so with that, I hope everybody has basically a nice morning, afternoon, and evening.
Yeah.
Okay.
Thanks.
Thank you very much.
Thanks again, Geanina.
Thank you too, and it was really nice. I hope that I'm able to stick with you for a while, like with the seminars. Yeah, I think someone else has a question. I saw a hand.
Guillaume, are you applauding or are you asking a question?
Sorry, I got confused. I think I'm already sleeping.
Yeah, I think applause. Okay, well, thank you again for your talk. Take care.
Same here. Thank you so much. And yeah, have a very nice evening, morning, middle of the day, whatever. Whenever